All right, so in this lecture, we're going to talk about inflection points. And an inflection point is just a place on the graph where the function changes concavity, right? It's a change in concavity. So you're changing from concave up to concave down, or you're changing from concave down to concave up, all right? And if you recall, the concavity, we can determine the concavity of a function at any given point by looking at the second derivative at that point, all right? So if the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down, all right? So concave up, I usually think of it looks like a U. Concave up, the curve of the function looks like a U. So it could be concave up and decreasing, or concave up and increasing. All right. Concave down looks just the opposite, upside down U, right? So this is what a concave down function looks like. Concave down. Oops. Down. And it can be concave down and increasing, or it could be concave down and decreasing. Okay, so this diagram just shows an example of, on the left here, we've got an increasing function. So it's increasing everywhere along the curve, right? The function is increasing everywhere along the curve. So the first derivative is positive, but it's changing concavity. So down here, it looks like the slope is increasing, so it's concave up. Up here, the slope is decreasing, so it's concave down. Okay, and then this other example on the right here is just showing you a decreasing function. So everywhere along this curve, the function is decreasing, right? But it's at the beginning here, on the left of this curve, is the slope is becoming more negative, right? So the slope is decreasing because it's becoming more negative, so it's concave down. And then down here, the slope is negative, right? Because it's still a decreasing function, but it's becoming less negative. Becoming less negative means that the slope is increasing, so it's concave up. All right. So we're going to talk about how to locate an inflection point, and we can locate an inflection point just by finding where, or a possible inflection point, I should say, just by finding where the second derivative is 0. Okay, that gives you a possible inflection point. So it's a lot like finding critical points. And in fact, it is a critical point for the derivative, right? Because the second derivative is the derivative of the derivative. So you're essentially finding a critical point for the derivative. And if it's 0, that's a possible inflection point. And then we just need to test it. We need to test it to see if it actually is an inflection point. All right, so let's take a look at example 1. So this is actually the same function that we were using in the last lecture. X cubed minus 9x squared minus 48x plus 52. All right, and now we just want to find the inflection points for this function. So we can take the first derivative, right? It's our first step, is just to take the first derivative. So we get 3x squared minus 18x minus 48. But in order to evaluate the inflection point, or find the inflection point, we need to know something about the concavity, which requires us to take the second derivative. Okay, so that's the derivative of the derivative. I get 6x minus 18. All right, and to find a possible inflection point, I'm just going to set that equal to 0. And I can find that there's a possible inflection point. So I'll write this down. Possible inflection point at x equals 3. All right, because if I plug in 3 for x, I'll get 18 minus 18, and that's 0. Okay, so that's a point where the derivative, or the second derivative, is 0. But we don't know for sure yet whether it's an inflection point until we test it. And how do we test it? We can just test the second derivative on either side, just like we did in the last lecture on critical points, to find out whether a critical point was a local maximum or minimum. We could just test points on either side. So in this case, we're testing to see if there's a change in concavity, right? Because that's what That's how we defined an inflection point. It's just a change in concavity. And so what we can do is we could look at the second derivative at 0, because that's to the left of 3, right? So and that's an easy point to just plug in to the equation, because if I plug in 0 into the second derivative, I get 6 times 0, which is 0, and then minus 18. So the second derivative at 0 is less than 0, which means that the function is concave up, or sorry, concave down, down, right? If it's negative, it's concave down. All right, and then we'll check a point on the other side. So a point on the other side of 3, I could choose like 4. All right, so if I plug in 4, 6 times 4 is 24. So 24 minus 18 gives me, what, 6? And that's greater than 0. So that means on the other side, it's concave up. So there is a change in concavity. That means that there's an inflection point at, inflection point at, actually, inflection point, I should probably just write it all out. Inflection point at x equals 3. Okay, so there is indeed an inflection point because we tested it, and there's a change in concavity. All right, so that's not too bad. I'll meet you in the next video.